So is it pretty clear what I'm asking you to do? This isn't a quiz. As I understand it, that's moving at a constant velocity along a level surface that is experiencing no friction. It's going to encounter a section that has a coating on it that will create a drag force that is proportional to the square of the velocity. When that occurs, it will be experiencing an unbalanced force. I'd like you to use that information to create a differential equation that could be used to solve for an expression for the velocity as a function of time. And then I want you to see if you can solve it for the velocity as a function of time, or at least see how far along in the set of steps that you have that you can make it to during that. So I would expect that at best you get to a function. At worst, you get stuck at the point where you're applying the boundary conditions and putting the integral symbol out there. That's kind of what I would expect you to be able to do. Now, realistically, how long should I give you for this? Now, in the old version of the test, this would probably all be worth about 3 points, which means 3 minutes, right? Point a minute, 45 points in 45 minutes. But your new test, more points because it's 4 questions, but way more minutes. But I still think, A, lots more words are going to be here on your test. They're going to use a lot more language. But B, I think you're still probably going to have to get this kind of done in like 3 to 5 minutes. But I'll say you're novices at it. How about we go with like 7? Somewhere in the middle between your suggestion of 2 or 3 and 10. I'll go with 7. I'll set a timer. And I'm not going to help very much in the beginning, but I'll walk around after about 5. Give it a try. It's not a quiz. Work together. Set a timer for 5 minutes. All right. For the most part, this is not very different from what we did yesterday. In fact, I'd argue that it's easier in many ways. But a lot of your final solutions, as I walked around, those of you who were able to get there, make it difficult to see the functional dependence. And that word, and we've used it before, functional dependence. It's also going to make what I'm going to ask you to do next a little bit more challenging. If I asked you how the velocity changes as t changes, does your equation lend itself particularly well to that? Now, some of yours do, some of yours don't. There's ways to make what some of you have there much easier to read. So let's talk about, where do I start when I'm trying to make a differential equation? All of you started somewhere. Where did you start? Go ahead.
I just used the fundamental physics concept.
Which one?
Net force equals ma.
All right, net force equals ma. It's a good place to start. And the reason it's a good place to start is why? Go ahead.
It contains a differential in it.
It already contains a differential in it. More importantly, or I would say additionally, not more important, additionally, that differential is a differential of velocity and time, which is what was in the question. Now, our problem actually begins when a box makes it here, and it's at that instant that a unbalanced force acts on the box in this direction. Right, so we're setting this as t equals 0, the instant that we have an unbalanced force acting on the box. So, were you successful in parsing out our expression here and dealing with it correctly? I'm going to make this direction the positive direction. Although there is a negative sign in this formula, I need to impress upon you that that negative sign is telling you direction, but it doesn't know anything about left or right. what it says is that the drag force is in the opposite direction of the velocity. That's what it states, right? This negative sign is indicating that the direction of the force opposes the direction of the velocity. This symbol, the V with a little hat on it, is a unit vector in the direction of the velocity. It has to be there, or something has to be there to indicate direction, because velocity is squared. So its vector component disappeared the moment we squared the velocity. So the reason why the symbology is there is to reestablish the direction, so that we understand that force opposes the direction of motion. So when we've had other expressions in the past, like this one, the velocity wasn't squared, there was no function attached to it, so it retains its direction. Does that make sense? Same with, right, the x there retains its direction. I don't have to make a statement about the direction being some other vector, but in this particular function, because the velocity is squared, I'm adding something here to remind us about the direction. But it just tells me that it's in the opposite direction of the velocity. Since the velocity is positive, I'm going to make our drag force in the negative direction, since our positive direction is the direction of the velocity. You follow why I'm making it negative? Not just because it's in the formula, but because I set the right to be the direction of positive direction, and that's the direction of the initial velocity of the box. Now, all you had to do to get part 1 was to sub in that differential. And you've successfully gotten your 1 point, maybe 2. It's not, it would not be too far-fetched for them to give you up to 3 points for deriving a differential equation, but I wouldn't expect more than 2 on the test. What now? We don't need any of that anymore. What now? Go ahead.
Separate your variables, so divide both, or multiply both sides by dt and...
All right, that's good. We'll start with one step at a time. We could isolate ahead of time if you prefer, or we can just go ahead and begin this process of separation. Makes no difference to me. They're basically the same math. So since Ignacio raised his hand, I guess he gets to decide. So we're going to just do separation. So we have successfully split the differential. Somebody else tell me what we do next. Go ahead. Luke? Collect terms. I don't see an expression for t, but I do see an expression for v. I don't have to do very much here to collect terms. I just have to divide both sides by v squared. All right, somebody else tell us what we do next. Go ahead. Well, I'm going to do something first, but I can put the symbols up there to indicate that I'm going to perform the integral. So I can integrate both sides. But this part is critical to me. We need to set our boundary condition here. So what are our boundary conditions? Somebody want to offer me up the boundaries for one side or the other? Go ahead.
0 to t for dt, and then v naught to v for dv.
All right, so here's the first mistake I started seeing out there on the floor. The object did not have 0 velocity at time 0. So I saw, a collection of 5 or 6 of you who assumed that the initial velocity was 0 at time 0, but it wasn't. The initial velocity is v naught. Our example yesterday, the initial velocity was 0, but at time 0, the box is sliding at v naught. I don't want to make this statement, but I have to. This is not v times t. I'm saying it because there's some people out here who believe this, and we need to work on that. Right? We need to understand that this symbology is just saying v as a function of t, but not v times t. And I get that it looks exactly like v times t. It's context, correct? The context in which this is being used is we're indicating that we're looking for the function of the velocity as a function of t. Now, I'm not going to use that symbol very long. I put it here just as a reminder that we want our functional dependent variables in our antiderivative. Right? We want them clearly articulated here. Now, there's a different way to do this, and some of you are already aware of it, in that you know that you can do this as an indefinite integral, get a constant, and then put your boundary conditions in after you integrate. Every single solution guide that I get from a college board wants to see the integral symbols with your definite integrals in place. So please do this. Now, here's where, in our prior discussion, I think you guys need a little bit of help, but this one is easy. I mean, this is just a polynomial function. So my expectation is that you could have gotten to the end. The issue is what you did with your algebra towards the end that I think is a problem. Now, don't get me wrong, I walked around and saw lots of mistakes for the next couple of steps. So not everybody can do this. So let's consider the left side first, because it's the easiest. There's no t there, but I'm not going to spend all the time talking about the t to the 0 power that's implied. I'm just going to say the left side is ct being evaluated from 0 to t. Any questions? The right side, the m is just a constant. It can come out front. So I think you're all pretty aware of that. We're talking about a polynomial. I know 1 over v squared, but it's v to the negative 2 power. So the antiderivative of v to the negative 2 power follows the polynomial rule. I add 1 to the exponent, divide by the new exponent, and I'll get negative v to the negative 1 power evaluated from v naught to v. Most of you got this. 2 or 3 didn't, but most of you got it. Minus ct on the left, and m times negative, and I'm going to just do 1 over v minus 1 over v naught. Pulling out that negative sign lets me do this. And I think that's just fine. Alrighty? I had to solve this for v. I think it's not a bad idea to go ahead and get that m over here for now. And I'm only writing out these steps because what happens in a moment bothers me, because it loses you your opportunity for functional dependence. How many of you just added 1 over v naught to both sides? That's not very many. That means that not many people made it to this part. I saw more of you make it here. If we do that, it's not terrible. It's what a lot of you did next that I think is tough. It's really hard to see the functional dependence in this. But that's what a lot of you did, and stopped there. Can I suggest a different way of doing your functional dependence? If you're going to have to invert something that's already a couple of maybe complex fractions, I would strongly encourage you to get common denominators first and treat it as a single fraction. So that's what I want to do next. I want to get common denominators. And I'll have v naught ct plus m. Okay, common denominators. Any questions about that? Now when you invert both sides, the functional dependence is so much easier to see. First, let's talk about the t equals 0 case. Do we get the expected outcome for the velocity at time 0? I think we do. And if you don't know what I'm saying, I mean, put 0 in for t, and this whole term goes away. And then I have m v naught over m. The m's cancel, I'm left with v naught. That makes sense. A few other things. When t gets really, really big, is it really clear that our velocity gets small, approaching zero when t goes to infinity? All good. It's an inverse relationship though, so it changes different than an exponential relationship like we saw yesterday. So our system will go to zero, but does it ever really approach zero? Yeah, technically no, but yeah, we know it probably will actually stop in the real world. There's not a whole bunch else here, but things like what m has to do with our answer and what our initial velocity has to do with our answer, those are a little more muddy because they appear in more than one place. But I think it should be pretty clear that increasing the initial velocity doesn't arbitrarily just mean that you're going to have a longer period of time until the velocity goes to zero, because it's on both top and bottom, right? So because the force is velocity dependent, hitting that patch faster doesn't necessarily mean it takes longer to stop. Do you notice that? I think that's important. Similarly, the mass has a similar functionality to it. Having a heavier object, this force is still capable of stopping it. It's on both the top and the bottom of the fraction. Here's why I think it's a good idea to do this too. What if I want position as a function of time? This one's going to be easier to work with than what you had before. Can you see that? Now, I think finding position as a function of time here is challenging. It also tells us where the object stops though. And we should get a pretty good impression of where it stops. Now, this is a harder thing to do, and our time is somewhat limited. How many know exactly what I'd be asking you to do if I said, please find position as a function of time? Okay, that's a much smaller number. So if I wanted position as a function of time, it's already kind of embedded in there. You'd have to create a new differential equation. So what you would be asked to do, or tasked with doing, solving this differential equation. Now this one's a little more challenging. Not much, it's one we did yesterday, almost identical to the one we did yesterday. So you'll find that the answer is not particularly hard to get to if you follow the steps from yesterday. The thing that you'd have to do is set some boundary conditions, like I'd want to go ahead and say that at t equals 0, we'll say that x is equal to 0. That the part where the stuff is 0 for our purposes of our for our integration. Does that make sense? What do you think? Think you can do it? Because I'll give you 3 or 4 minutes. So about all the time you should have to take for this one, since it's a point-for-point similarity to yesterday. Go ahead.
Could I ask, further above, what would be the issue with leaving the v naught out of the total fraction?
Like this?
No, right there.
This?
Yeah.
I don't understand, like flipping it?
Yeah.
Because you can't just flip like one fraction in an expression. So what you're actually doing is you're raising both sides of your equation to the -1 power, right?
Okay.
So we do get, and this is not a knock at what you just said, I think it's something that everybody should hear. We get complacent with what we're actually doing because we're taking shortcuts. So we all do it, but remember the boundaries of algebra, what we can do to both sides of an equation are pretty explicit. So we can raise both sides of an equation to a power. That's what we're actually doing. Similarly, when you cross multiply, cross multiplying is actually just the multiplicative property applied twice. Right? We're multiplying two things that are equal to both sides of an equation. So it's one of those things where we tend to forget these kinds of little details.
Thank you.
You're welcome. So first thing, that's what I'm gonna do first. Look good for you guys? All right, then next thing I'm gonna do is integrate both sides, because I already have everything where I need it to be. And this side, 0 to some place in the future, and this at time 0, we're still starting from v naught, right? Its velocity isn't 0. And, I'm sorry, what am I saying? Not v naught. We're starting at time 0, and we're going to some time in the future. All right, so don't want to spend a whole lot of time because we don't have it. So I think I'll speed through the left side, and I'm going to pull out my mv naught here, because again, just a constant. My u sub will be v naught ct plus m. Du dt is going to be v naught c, and du v naught c dt. So dt is 1 over v naught c du. All right, just like a process from yesterday. Are we all good? Going fast, I know. This is just going to be a constant. So when I sub it in to save me space, I'm going to write m v naught over v naught c and the integral of 1 over u du. Everybody okay with that? You guys see what I've done? All right, on to the last couple steps. M over c, and I don't have an integral anymore, but I do know that this will be the natural log. And remember, we know what u is, so we can just sub u right back in here. V naught ct plus m evaluated from 0 to t. Now, when I evaluate that, I get natural log of v naught ct plus m minus natural log of, well, just m. Now, I don't have to solve this for t, right? It's already here. In the last one, we had to solve it because v was trapped in here. This side is just x, but it might be cleaner to combine them. Again, you don't have to, but it might be cleaner. Part of the reason why it might be cleaner, I don't know if you know why this looks better, but a lot of times in a function, if you can do something like this, it looks better. Okay. It removes that m over m that was there before and gives us a better understanding of the functional dependence here. You follow me? All right. Logarithmic function, does that make sense here? We should plot it, see what it looks like. But I think it makes sense here. When t equals 0, we get the natural log of 1, right? Giving us an idea of what we would expect, right? So it gives us x equals 0. And t, when it gets really big, does it do what we think it's supposed to do? Does it go to, it's not going to go to 0. We wouldn't expect it to go to 0 because the object doesn't come back to 0. It goes somewhere.